Evening, boys and girls. It's another lesson on Technical Sciences Grade 12, and we are still continuing with momentum and impulse. And we have really done well throughout the course of the week because we have really went deep into everything that momentum and impulse entails, because we were guided by our examination guidelines. So I want to believe that if you understood everything that we did this week, then you are well on your way to doing very, very well in your preparatory examination as well as your final examination. So my hopes are up, and I hope that yours are up. So in today's lesson, because we have done the entire theory behind momentum and impulse, and we have done questions on various aspects of momentum and impulse, then I decided that today we are definitely going to deal with more questions on momentum and impulse, and we are taking these particular questions from your previous examination guidelines. Remember, I still want to assist you to see how we mark and to see how we are expecting you to present the question, rather to present your answer in order for you to be able to obtain your full marks. And there are some aspects where a learner also answers fully, but at some point the learner does not answer fully, and yet you find that you actually know the answer. So I'm going deep down today as well to show you the extent to which you need to be able to answer your questions in order for you to obtain your full marks. Remember, my dear learners, we want you to do very well. We want you to get your level 7s, and hence we are doing these particular shows for you. So these are the questions, and I just want to also give you a brief overview that these particular questions, you will see they encompass basic calculations on momentum, which is what is expected of us as per the examination guidelines. And from being able to calculate momentum, then we are getting questions that test our knowledge on momentum, how momentum changes, and how it impacts on the velocity of the object and so on. So we will be dealing with that. And furthermore, our questions now will be talking to impulse, and we will be trying to understand impulse better by understanding the impact of the net force, the impact of the contact time, and how impulse relates to the change in momentum of an object. Then we will go further on to answer questions that are theoretical, that require deep insight and application for us to be able to see whether you understand momentum and impulse better, and how each variable affects the other one. For example, how the mass of the object affects the momentum of an object, how the velocity of an object affects the momentum, and how the contact time will affect the net force acting on an object, as well as the velocity that is acting on an object. So we will be looking into those type of questions. And further on, based on our examination guidelines, we will then be looking into questions that address the principle of conservation of mechanical energy, where we will learn to determine either the momentum of an object before the collision or after the collision, or rather the velocity of one of the objects before the collision, or the velocity of the other object after the collision. So we will be working on those type of questions. But furthermore, I want to teach you how to also read in between your scenarios that are given, for example, here, and to relate it to the diagram that you have. So let us go straight into the question. This question was taken from the technical science control test in the Free State from the year 2018, and I want us to really look at this particular question. It's really, really interesting, right? So they tell us then that we have two ice skaters and they are at rest. Now remember, when we say they are at rest, it definitely means something for us in technical sciences. So two ice skaters are at rest on an ice skating rink. Then they push horizontally against each other's hands, and due to this, they move away from each other. Their masses are 90 kilograms and 60 kilograms. The 60 kilogram skater moves away with a velocity of 3 meters per second, while the other one moves in the opposite direction with a velocity of 2 meters per second. Right, so let us look at this particular scenario and basically learn how do we take what is given on the scenario that we are reading and the diagram. So we are then told that we have two ice skaters and we can see the ice skaters, and we are being told that they are at rest. We know now if they are at rest, it means that the initial velocity of each is definitely 0 meters per second, right? And also for the 60 kilogram skater, the initial velocity is going to be 0 meters per second, right? So there are your ice skaters, they are at rest, and the initial velocity is 0 meters per second. They push horizontally against each other's hands, and due to this, they move away from each other. Now, what does this tell us? They tell us that if they are pushing horizontally against each other, then they are exerting a force on each other. And it makes sense. Now, when we look at this particular skater, it means the 90 kilogram skater is pushing the 60 kilogram skater to the right. And then the 60 kilogram skater is pushing the 90 kilogram skater to the left. So they are exerting forces on each other through their hands. And we've been given the masses there, and we are happy the mass is in kilograms, the mass is in kilograms, so we don't need to do any conversions. Then the 60 kilogram skater moves away. So he moves away with a velocity of 3 meters per second. And then the other one, and this one, obviously now it means it is the 90 kilogram skater, moves in the opposite direction with a velocity of 2 meters per second. So basically what we can see here is that at the beginning, she was stationary, she was also stationary. And if she was stationary, it means at the beginning, the initial velocity is 0, and therefore the 90 kilogram skater does not have a momentum at the beginning, right, before the collision. And also the 60 kilogram skater does not have a momentum at the beginning, right, because she was also stationary. But after exerting a force on each other, in other words, after colliding with each other, then they now have a velocity. So if they have a velocity, then they now have a momentum, because we can get the product of the mass of an object and the velocity. we can get the product of the mass of an object and the velocity. And that is definitely going to give us the momentum after the collision for each of the skaters. So that is essentially what you should be able to see. Now, we've been asked in the questions now to define the term momentum. Now, this is 2 marks. Now, how do we define the term momentum? You will remember, basically, momentum is given by this formula, P is equal to M multiplied by V. And from the formula of momentum, we can actually get we can actually determine the velocity of an object, or rather we can determine the definition for the momentum of an object. And because this is momentum and we can see this equal to mass multiplied by velocity, it means that momentum is then the product of the mass of an object and its velocity. Or someone can say it is the product of the object's mass and its velocity. And that is how we will define momentum. You just look at the formula and say, oh, I'm multiplying mass with velocity. In other words, momentum is the product of the object's mass and its velocity. And with that, we are going to get 2 marks. And you can see there, my dear learners, it is 2 marks or nothing. It is the product of an object's mass and velocity, and that gives you 2 marks or nothing. Then we are asked, what is the magnitude of the total momentum of the 2 skaters while they are at the rest and before they have pushed against each other? Now, this question is for only a single mark, and we are asked, what is? So immediately when they ask us what is, and we check the allocation of what, it automatically tells us that we actually don't need to be performing a particular calculation. Why don't we have to perform a particular calculation? Because the question says what. It means from our theoretical background, we can be able to answer this particular question. And remember, we want the magnitude and we want the magnitude of the total momentum, right? And if we want the magnitude of the total momentum, it means we want the total momentum of the 2 skaters. Now, while they were at rest. Now, when they were at rest, the initial velocity of the 90 kilogram skater is 0, because that is what the rest means. The 60 kilogram skater, it was 0. So if the velocity is 0, then the momentum is 0. If the velocity is 0, then the momentum is 0. So if you add the momentum at rest for this skater, which is 0, and you add the momentum of the second skater, which is 0 as well, just when they were at rest, then the total momentum is 0 plus 0, and it will give you it's quite simple. The momentum, or rather the total momentum while they were both at rest, is definitely 0 kilograms dot meter per second. Then for question 4.1.3, we are being asked to show by means of a calculation that the total momentum of the 2 skaters is equal to 0 while they move in opposite directions after they have pushed against each other. So we must show by means of a calculation. So we are going to perform a calculation there. And we want to show them that the total momentum of the 2 skaters is equal to 0. Now, my dear learners, this question is already guiding us to say that the momentum of the 2 skaters is equal to 0 while they move in opposite directions. Basically, that is after they have pushed against each other. So what we need to understand here is that the total linear momentum after the collision, after pushing against each other, is also equal to 0 kilograms dot meter per second. Now, when you perform a calculation and you see that it's not giving you 0, then you know that you have definitely made a mistake. And how do we know that? Because they have told you that it is definitely equal to 0. So yours is just to basically prove that. Now, what lesson am I getting here? The lesson that we are getting here is that the total linear momentum before they pushed against each other is 0 kilograms dot meter per second. And the total linear momentum after they pushed each other, they are also telling us that it's 0 kilograms dot meter per second. So what else are we learning from this particular instance, from this particular question? We are definitely learning here that the system is isolated. And why can we conclude that the system is isolated? Because we know that the total linear momentum of an isolated system is conserved. So in principle, in other words, the total linear momentum before the collision is equal to the total linear momentum after the collision. So if the total linear momentum before the collision is 0 and the total linear momentum after the collision is 0, it means the total linear momentum remains constant. And if it remains constant, then it tells me that the system is isolated altogether. Now, what else are we learning here, my dear learners? Remember now, when we then think about an isolated system, then we remember that we need to be able to define the term isolated system. And when we define the term isolated system, we say it is a system whereby the net external force acting on the system is equal to 0. So it is a system whereby the net external force acting on the system is equal to 0. Now, that is what we definitely mean when we talk about an isolated system. So a lot of things should be coming into your head as you do these questions, because you don't just want to stick to the question, you are revising in this particular instance. So you should be able to pick up some of the things that are happening here in between. So how are we going to approach this particular question? We just want to prove that the total momentum of the two skaters is equal to 0 while they move in opposite directions after they have pushed against each other. So if we want the total momentum after the collision, it means I just have to add the momentum of skater 1 with the momentum of skater 2 after the collision, and I must be expecting a value that will give me 0 kilograms dot meter per second. Now let's see how we would approach that particular question. So remember, this is a scenario after pushing, right? So this actually happens after pushing. It happens after pushing. So after pushing, we then want to show that the total momentum of the two skaters is 0. So after the collision, P is equal to P1 plus P2. We definitely know that that momentum, which is represented by P, is the total momentum, but this is the total momentum after pushing. So it will be the momentum of skater number 1 plus the momentum of skater number 2. Then we know that we have to break down momentum. And we know that momentum is the product of the mass of an object and its velocity. So that will be for trolley 1, and the same is going to apply for trolley 2. Now, we deal with, rather, skater number 1. I'm so used to dealing with trolleys. Remember, here we are still dealing with skaters. So skater number 1, which is the skater on the left, has a mass of 90 kilograms. And if we choose, according to this scenario, we choose to the left as negative and we choose to the right as positive, then remember here we are substituting velocity, which is a vector quantity. So to the left, it's a negative. Why? Because we chose to the right as positive. Then we are done with the momentum of skater number 1. Then we say plus, then we go to the momentum of skater number 2. Then the mass of skater number 2, it's 60 kilograms multiplied by the velocity of skater number 2 after the collision, it's 3 meters per second. But remember that 3 meters per second is positive altogether. Why? Because skater number 2 was moving to the right after pushing. Then you do your mathematics. 90 times negative 2 gives you negative 180 plus 60 times positive 3, it gives you positive 180. So in totality, negative 180 plus 180 is going to give you 0 kilograms dot meter per second. So we award you 1 mark there for the correct formula that shows us that you are calculating the total momentum after the pushing has taken place, after they have pushed each other, and also for the substitution. No mark there because you were basically being given the final answer. But remember, we won't be awarding you a mark for substitution if we don't have a mark for the, rather, if you do not indicate the final answer. So this is compulsory. It is compulsory for you to show us this because you are proving. So you need to go to get to a point where you show us that that value is definitely 0 kilograms dot meter per second. So you are definitely compelled to do that. Otherwise, you won't be able to get a mark for substitution. Even if the substitution is correct, but you have not shown us the final answer. Then option number 2 here, my dear learners, everything is the same. It's just that here we choose the left as positive, and hence the 2 was substituted as positive 2, and the right is the negative, and hence the 3 meters per second was substituted as a negative value. But we get to the same answer altogether. And these are exam type of questions. So I'm really expecting you to do well and to really be able to interpret the questions and get the marks, all the marks in fact. Now, let us go to another question. The next question there, it says, a tennis ball with a mass of 60 grams. So the mass there is 60 grams. Approaches a tennis player with a velocity of 6 meters per second. So let us look at the information that was given there. This is what we see on the diagram. So there we have a tennis player, and she is definitely holding a racket. And now a tennis ball is approaching her, right? And she will most probably hit it, and it will go back in the direction where it came from. So there, it was going to the left as it was approaching her, and then most probably the tennis ball player will hit it, and then it will go to the right. Right, but let us not assume, and let us go to the questions. Now, we are required to define the term impulse. Now, by definition, Impulse, we say, it is the product of the net force acting on the object and the time the net force acts on it. So, impulse is the product of the net force acting on an object and the time the net force acts on it. So when you look at this, right, which you can actually get from that formula, the impulse momentum theorem formula, where we see F net delta T is equal to delta P. And we definitely know that this entire thing, right, F net multiplied by delta T, it represents your impulse. So impulse is the product of the net force acting on the object and the time the net force acts on it. That is why it's F net multiplied by delta T. And the fact that we are taking F net and we are multiplying by delta T, then we are definitely getting what we refer to as the product. So you can't omit the word product. It is the product of the net force acting on the object and the time the net force acts on it. So that is essentially that, and it will be for 2 marks. So let us see how we actually allocate marks to that particular question. Right. Then so we say it is the product of the net force acting on an object and the time the net force acts on the object, and that we get 2 marks. Now, my dear learners, where we say impulse is defined as the change in momentum, you know, it's not the main definition of impulse. The main definition of impulse, it's this one: the product of the net force acting on an object and the time the net force acts on the object. And this one is the one that you get on your examination guidelines. Now, the sole purpose of actually showing you this is to say, I'm well aware that you get hold of this marking guidelines and you see impulse has been defined as the change in momentum. Now, impulse is actually equal to the change in momentum. It's not necessarily the change in momentum. It is equal to the change in momentum. So stick to the definition that is in your examination guidelines, which is this particular definition there altogether. And again, we can see that it is 2 marks or nothing. In other words, all these keywords, the product of the net force and the time the net force acts on the object, if you omit any of those, then we lose the meaning altogether. We lose the meaning and you get 0. So this is not part marking. Everything is 2 marks or nothing. And hence I told you the direction that we are really going into in terms of marking definitions as well as principles. Then we go to the next question. Right, sorry, it was just a little bit slow there. Then they tell us the tennis player hits the ball in the opposite direction with a net force of 5 newtons. Right, so the tennis player is hitting that particular ball and it moves in the opposite direction. Now, if it moves in the opposite direction, it means it is going against the direction where it actually came from. So when it was approaching here, it was going to the left. It means when it goes in the opposite direction, that is when it is going to the right. Then they tell us the ball is in contact with the racket for 0.1 second. So there it means we've been given a value for delta T, the contact time, the time with which the net force is acting on the tennis ball, or also the time with which the net force is acting on the tennis racket. Now, we've been asked to calculate the magnitude of the velocity at which the ball leaves the racket. So here, we just want the magnitude of the velocity. Remember, velocity is a vector quantity. So you actually need to give us magnitude and direction if we asked you to calculate the velocity. But because we just said calculate the magnitude, it means we are not asking you to also add direction. So by just giving us the magnitude, then we will be fine. Now, I want you to actually just check what you have. According to this, we've been given the value for delta T. Then we've been given the value which is the net force. So we've been given the value for F net. Again, we've been given, remember, we want the magnitude of the velocity at which the ball, and then with the ball, we can see that we've been given the mass of the ball. And again, it was approaching the tennis player with a velocity of 6 meters per second. So we've been given the value for VI because this is the velocity before the collision. And now we are asked to calculate the magnitude of the velocity at which the ball leaves the racket. So this particular velocity, when it was going in the opposite direction, which is VF. Now, based on this, I am sure you can definitely see that we have everything. We have F net, we have delta T, and we have F net, we have delta T, and for delta P, we can actually calculate, okay, for delta P, which is given by MVF minus MVI. Then we can see we have the mass. Happy with that? We have the mass still. We have the initial velocity. So we can get the final velocity, right? VF, we can get the final velocity, which is this velocity when it leaves the racket. So this formula is definitely going to be relevant. Then let us answer that. Now, for option 1, we'll say F net delta T is equal to delta P. This is a formula that we get in our examination guidelines, or in particular, we get it from our formula sheet. Then we know again, you can see there that delta P has been broken down into MVF minus MVI. So F net delta T is equal to MVF minus MVI. How do you know that you need to break it down into that? Because you will see again in your formula sheet that delta P is given as MVF minus MVI. It means where you see delta P, you actually see MVF minus MVI. And hence, where we see delta P, we have MVF minus MVI. Then we've been given the value of the net force, which is 5. Remember, for this particular option, we are choosing to the right as positive. And the tennis racket exerted a force on the ball, and the force on the ball was acting to the right, and hence the net force is calculated as a positive 5 newtons. The contact time is 0,1. Now the mass here is 0,06 kilograms. Remember now, the mass of the tennis ball was given as 60 grams. Now you can't substitute your value in grams. You need to take it to kilograms. In other words, you have to divide by 1,000. Now, if you divide by 1,000, 60 grams divided by 1,000 will then give you 0.06. But this is going to be in kilograms. Now, if this is in kilograms, then we have done our conversion, and then we have VF, which is what we are looking for, minus the initial velocity. Now, the initial velocity, remember, that's when it was going towards the tennis player. And that was at 6 meters per second, and it was to the left, and hence we substituted a negative. Then you do your mathematics there, and you can see that VF will then give you 2.33 meters per second when it is rounded off to 2 decimal places. Are we together? Right. Now, 1 mark there was on the formula. 1 mark was for the correct substitution of F net and delta T, which is the impulse, by the way, and 1 mark for that particular mass, and obviously now when it has been converted to kilograms, and 1 mark for the substitution of the change in velocity that took place. And then the final mark was for the correct magnitude of the final velocity. Option 2 is the same one, it's just that we are choosing to the left as positive. In other words, to the right is then negative. Now, let us go into question 4.2.3. Now they tell us the next ball also approaches the player at 6 meters per second. In other words, this is still VI. This time, she exerts the same net force as before on the ball. Now, what was the net force before? The net force before was 5 newtons. Okay, so the tennis ball is still coming at 6 meters per second. The net force that the racket exerts on the tennis ball is still 5 newtons. But for a longer period, in other words, if we say a longer period, that time period there refers to time. So it means now delta T is actually being increased. So we are applying the same net force, but for a longer period of time. Will the magnitude of the return velocity of the ball be greater than, equal to, or less than the answer to question 4.2.2? Now, my dear learners, if we say, and I want us to really test it. If we say F net delta, okay, let us put it in this fashion. Okay, now I'll continue this way. Let's say we say F net delta T is equal to delta P, right? That's how we get it on the formula sheet. Now, we can take this and rearrange it and say F net is equal to delta P divided by delta T. Now, you can see that if I increase the contact time and I keep the net force the same, and there my delta P, which is MVF minus MVI. When I take F net and I multiply it with delta T, then if I now increase the value of delta T, because now I'll be applying the net force for a longer period of time, do you then agree with me that the change in momentum is now going to increase altogether? Now, when the change in momentum increases, what is going to happen to the magnitude of the return velocity? Obviously, now it tells me that the magnitude of the return velocity is also going to increase. Why is it going to increase? Because now, when I increase the change in momentum, remember the change in momentum is the final momentum minus the initial momentum. So if F net delta T has increased, then it tells me that the change in momentum has increased. And if the change in momentum has increased, it definitely tells me that the final momentum is going to increase. Now, if the final momentum has increased, it means that the final velocity has increased. So what I'm simply saying to you is, let us look at it from the first formula then. Remember, I am now increasing the contact time. So if I increase the contact time there, then it means this value of delta P is going to increase. Now, if the change in momentum increases, what does that mean? It means that the final velocity is going to increase, and that final velocity is the final velocity, or rather is the velocity after the ball has been hit by the racket. So it is the velocity after the collision. In other words, when we increase the contact time and we keep the net force the same, then the change in momentum is going to increase. And also if we keep the mass the same. In other words, when we increase the contact time, the net force is kept constant, the mass is kept constant, the change in the momentum will increase, and this means the velocity has increased. So there I referred to 5 things. I said if the contact time increases and the net force is kept the same, it then tells me that the change in momentum is going to increase. Now, if the change in momentum increases, it definitely increases because the mass is still kept constant, but the final velocity must be the one that is increasing. So that is how you would have got your 5 marks. It means when you answer this type of questions, my dear learners, you must be able to refer to the variables that will affect the magnitude of the return velocity, because some of these are a bit abstract for you, and you start asking yourself, but what are they looking for in explaining the answer by referring to relevant variables in the impulse equation? And here you've been guided. Actually, it wasn't necessary for them to tell you that you need to use the impulse equation. So you must then be able to say, okay, I want to know what how the velocity is going to change after the collision, the return velocity. So I then need to look at the variables that are going to be affected, which variables are changed and which variables are kept constant altogether. Then our answer there is definitely greater than, and hence we get the first mark. So how do we do this? We say it's a longer contact time for the same force. So the contact time has been increased and the net force has been kept the same. So even if you said there actually for the same net force, then you get a mark. And when you increase the contact time and the net force is kept the same, then you are going to have a greater change in momentum, meaning the change in momentum will increase, and hence you get another mark. And remember now, the mass is still kept constant. That is why we say for the same mass, then the change in velocity increases altogether, right? Then let us move to our last question. It says, a car of mass 1,920 kilograms is at rest at a traffic light when a truck of mass 3,300 kilograms and traveling at 20 meters per second collide with the car. Now, this is definitely not good news. No one wants to be hit by a truck or in fact get into an accident for that matter. The car is pushed into the intersection. It means just after the traffic light, and the truck continues with a velocity of 12 meters per second. So there is the scenario. So this is what was happening before the collision. The car was stationary because it was at rest. In other words, the initial velocity is 0 meters per second. So if I asked you what was the momentum of the car before the collision, you would say it is 0 because the object is at rest, it is stationary. But the mass of the truck before the collision, or rather the momentum of the truck before the collision, is a value that is far greater than 0 because the truck was moving. So this is the initial velocity of the truck, and remember this is before the collision. Then after the collision, we can see that the truck still has the same mass, but it's now moving at 12 meters per second. So this is the velocity after the collision. It's 12 meters per second, and it's still going forward, or basically to the right. And we do not know what the velocity of the car is after the collision. So that is definitely VF. Now, my dear learners, if you check this, this type of a collision, we can actually say it is an elastic collision. Now, again, I will remind you, what is an elastic collision? It's a collision where total linear momentum is conserved and total kinetic energy is conserved. It's not a collision where they separate, where the colliding objects separate. No, that's not how we define it. That is how we see it altogether. So we see that they have separated. In other words, the velocities after the collision are independent of each other. They could still be the same magnitude, but we are not sure. And hence, when I deal with the momentum after the collision, I have to separate the final velocities because I'm not sure if they were traveling at the same final velocity and in the same direction for that matter altogether. Then we are asked to define the principle of conservation of momentum. Sometimes they will use the term state the principle of conservation of momentum. And we know very well the principle states the total linear momentum of an isolated system remains constant in magnitude and direction. So the total linear momentum of an isolated system remains constant in both magnitude and direction, and that is 2 marks. Right, so there it is given. The total linear momentum of an isolated system remains constant in magnitude and direction, and you can see it's 2 marks or nothing. So the total linear momentum of an isolated system remains constant in magnitude and direction. Everything has to be there. Altogether, my dear learners, everything has to be there for you to get the marks. So we don't have part marking. Then the next question says, calculate the magnitude of the velocity of the car after the collision if the truck and car remain separate. So the fact that they are remaining separate tells me that this particular collision is elastic. So I'm looking for VF, right? So I will apply the principle of conservation of linear momentum, which says the total momentum before the collision is equal to the total momentum after the collision. That gives you 1 mark. Or remember, total can be replaced by that symbol, which says the sum of the momentum before the collision. Why are we saying sum? Because we are adding those particular momentum will be equal to the sum of the momentum after the collision. So that is 1 mark. Then before the collision, remember, it will be the mass multiplied by the speed of the car plus the mass multiplied by the velocity of the truck. Pardon me, there we talk to velocity. And it will be the same on the other side. So the momentum of the car before the collision, it had a mass of 1,920 kilograms. And remember, it was at rest. So the initial velocity is 0 meters per second. Plus the mass of the truck, remember, it's 3,300 kilograms multiplied by the initial velocity was 20 meters per second, and it was going to the right, and we chose to the right as positive, and hence we left the value there as a positive. So that entire substitution gets 1 mark. In other words, my dear learners, if you substitute incorrectly for momentum of the car, but substitute correctly for the momentum of the truck, you will forfeit the entire mark, and hence accuracy is very important. After the collision, the mass of the car is still 1,920, but the final velocity we do not know, right? Which is what we are calculating. And we are not giving it direction. Remember, this is a variable that we are solving for. So the algebra here is going to give us the direction. You can't determine, or rather you can't predetermine the direction before. Plus, after the collision, the mass of the truck is still 3,300 kilograms, but it was then moving at 12 meters per second. And it was still going to the right. So we get the magnitude of the velocity of the car after the collision to be 13.75 meters per second. No direction was given there. Why? Because we requested for the magnitude altogether. Right, so that entire substitution is also going to get 1 mark, and the final answer with the correct unit will give you another mark. So my dear learners, it is so important that you are able to do these things. And you know, even our values must give us an idea about whether we are correct or not. And remember now, I'm expecting the velocity of the car to increase, right? Because it was pushed by the truck. And then I'm expecting the velocity of the truck to then decrease, and hence it actually, before it was moving at 20, but after the collision it was moving at 12 meters per second. So this was actually a very beautiful question that really required us to use our knowledge in terms of everything that the examination guideline requires us to know. So please really be aware of this particular type of questions. So I have definitely enjoyed this particular lesson, and I hope that you have learned something in terms of how your answers also need to be presented. I will see you again tomorrow, same time, same place. So enjoy the rest of the evening. Just before that, remember momentum and impulse. For those that are catching our show for the first time, it's going to be plus minus 22 marks. So be able to work on this particular topic because it carries a lot of marks. Right. Thank you so much and enjoy the rest of the evening. Goodbye.